acceleratorlab.gov. And if you don't get immediately a response from me, email me again. So we can ask a general question regarding symmetry and physics. We can ask, what are the symmetries of the laws of physics? And actually, this was sort of a new way to think that started in the early 20th century. And really, it was Einstein who pioneered thinking about nature in terms of symmetries. And you can ask the question, how do the laws of physics depend on where you are in space, where you are in time, what's your orientation in space, what's your state of motion? And in fact, we have, good experimental data on these things. We can, how could we determine whether the laws of physics are the same in the Andromeda galaxy as they are here on Earth? How could we get information about that? Well, you can look at the Andromeda galaxy, and you can just look at it through a telescope in your backyard. It looks sort of like the Milky Way, looks like other galaxies. Look at two galaxies and compare them, about the same size. That already tells you there's something similar about them. Yes, sir?
You can send a satellite there?
You could do that. How long do you think it would take to get to Andromeda galaxy? We could get the thing close to the speed of light. We'd still be, how far is it?
2 million light years.
Is it about 2 million? So that'd take, some very, very distant future civilization could get the data back again. No, the galaxy is sending the information to you right now. So it's sending you lots of light. And you can look at the light. And what do you see? And, I'm just going to editorialize it. It's great to have computer-simulated experiments. But you actually have to build them and do them to really appreciate what's involved. And one of the best possible experiments you can do just on a Saturday afternoon is build a Shoebox Spectrometer. All you need is a plastic diffraction grating. And I think you can order those from Edmund Scientific, or you can go to this American Science Center up here in Geneva and get them. And what you do is you take a shoebox and you make a little hole in the back, and you put aluminum foil over the hole. And with a razor blade, you make a very narrow slit. And that's what you're going to point at the sun. So what comes through through the slit is sunlight in the shape of a slit. And then on the other side, back side of the shoebox, you put another hole, and you put the diffraction grating there. Okay, so you've got the slit, and then here you've got the eyepiece, which is the diffraction grating. And you hold the thing up to the sun, being careful, the usual cautions, don't want to get direct sunlight into the eyeball. But if you now look a bit to the side, what you'll see is a beautiful prismatic rainbow splaying out of the sunlight, breaking it up into its colors. So the light's coming in like that, and you look to the side, and the diffraction grating will display the pattern there. And if you look carefully, by golly, you can see there are a lot of black lines cutting through that nice rainbow. And those are images of the slit that correspond to a precise frequency of light that isn't getting to us from the sun, because the corona, all that gas surrounding the fireball, is absorbing that light. So you immediately can, with $1 diffraction grating and a zero-cost shoebox, observe something absolutely profound, the absorption spectrum of the sun. And then you can do this to a street light at night, sodium vapor light. And if you want to start getting imaginative, you could do it to a fluorescent light. You could start looking at different things. And what you'll see always are the patterns of the atomic absorption lines, the electrons jumping from well-defined quantum orbitals to another, well-defined energies, eating up the light. Or in the case of a sodium vapor light, you'll see bright lines, because there you're seeing the specific electron transitions in the sodium vapor emitting the light. So I believe the Shoebox Spectrometer is the most interesting homebrew experiment you can do. And I was so appalled a few years ago when I went to the internet, this vast, incredible source of all knowledge. And I couldn't find a simple project plan for a home built spectrometer. I was just amazed. So we got to put one of those on the web, and you got to do that experiment, and you got to really do it, because you can look at pictures of this and you can see it simulated, but you got to actually make one, and you get then a better one if you use a better razor blade, and you can maybe eventually have an adjustable slit, and then refine the optics, put the thing on a tripod so it's better mounted there. Try to take pictures of the spectrum. Pretty soon you're really building a scientific research program of inquiry. I remember some guys when I was in high school who went to won the state student science fair by building a spectrometer that allowed them to see the Doppler motion of the rotation of the sun. And it was built with plywood and put together and tuned carefully, constantly. They had to take pictures and project them to blow the image up to see small little displacements of the spectral lines to catch the motion of the gas. And they won first place in the most honorable thing you can win in the State Student Council Illinois State Science Fair at that time, way back in the 60s. So that's something you should do. It's a really hands-on thing. Well, we can look at the spectral lines of light coming from Andromeda, and quantum mechanics tells us that those are measurements of the electron charge, the mass of the electron, the atomic nuclear charges. It's measuring the Planck's constant. It's measuring the speed of light. And we can check that those are the same as they are here on Earth. And we can do that for very distant objects, quasi-stellar objects, etc. And what we find is, subject to experimental errors and even some tantalizing controversy about whether it's true or not at a very subtle level, that the world is the same in Andromeda, in that region of space, 2 million light years away, or whatever it is, as it is here. And it's true all the way across the universe. As I say, there actually are nowadays some very precise measurements of certain things like hyperfine splitting of atomic levels in very distant gas clouds that seem to be, according to some people, showing a discrepancy with what we see here on Earth. But that's a controversy, and it'll get resolved by further measurement. And that's very exciting if we found that the laws were different somehow, 1 Hubble diameter away from what it is here. That'd be really big news. Are the laws of physics changing in time? We see no evidence of it. Again, at a certain level of precision. Do they depend on our orientation in space? Well, here you sort of have to imagine, yeah, they do, because I drop something, it falls that way. But that's because the Earth is there. But if I'm in empty space, is there some intrinsic bias to the laws of physics that tells us there's preferred up, a preferred sideways, a preferred backward and forward? And we don't see any evidence of that. So these seem to be symmetries. How about our state of motion? This is what all the relativity hullabaloo is about. When you are sitting on Earth thinking you're at rest, you're actually moving. You're moving in the Earth's orbit, around the sun. But of course the sun is also moving. And of course the galaxy it's moving in is also moving. You don't notice any of these motions. And in fact, if you were on a different solar system, different planet someplace else, you'd be moving differently. If you're on that planet doing all of these experiments, building backyard spectrometers, measuring spectral lines of sodium vapor lamps, will you see a different spectrum on a different planet associated with a different star in a different galaxy that's moving at a much different relative velocity to us? Apparently no. We have an enormous amount of experimental evidence to show that the laws of physics don't depend upon the state of motion. In fact, if I do my lab experiments, I can go out into the universe and move around, and as long as this thing is just coasting inertially through space, even if it's falling into a black hole, you won't notice it, as long as the experiment is moving inertially. That's one of Einstein's other insights, is that free falling is actually inertial motion, but in a warped space, a warped space-time geometry, which is what gravity produces. So we have the symmetry that says the laws of physics are the same wherever you want in space, and that has 3 degrees of freedom, x, y, and z. Time is just resetting the clock. That's 1 degree of freedom. So time now, as opposed to tomorrow, you do Galileo's experiment tomorrow at noon, 2 masses that are different, you drop them, they fall at the same rate. Or you do the experiment next week, of Tuesday at midnight, and they'll fall at the same rate and they'll fall identically. That's 1 degree of freedom, the time. Orientation in space, 3 rotations. And state of motion, we call boosts. We can boost the system by giving it a relative velocity to us in any of 3 degrees of freedom. And here comes Noether's theorem. For every continuous symmetry in nature, there's a corresponding conservation law. For every conservation law in nature, there's a corresponding continuous symmetry. In other words, these symmetries are in one-to-one correspondence with dynamical, measurable physical quantities. And those physical quantities never change for any large experiment that itself isn't changing, a hermetic experiment. So for example, space translations, 3 degrees of freedom, corresponds, that symmetry corresponds to the conservation of momentum. The fact that the laws of physics do not change in time corresponds to the conservation of energy. I don't mean by conservation of energy reducing your energy consumption, which is always a good thing. I mean that the total initial energy in a closed physical system, no matter what happens, no matter what forces are involved, pions interacting with nucleons, quarks interacting with gluons, atoms forming molecules, whatever, the total energy will be the same after as it is before. If we rotate the system in space, that's a symmetry, and that corresponds to the conservation of something called angular momentum. If we put the system in a different state of motion, we find that we actually have to talk about a generalization of angular momentum, which has its own 3 degrees of freedom, called relativistic angular momentum. And that's a bit tricky. So it's tricky because actually in classical physics it's always 0. It's very hard to observe the consequence of this, but it's generally a part of angular momentum as a statement of relativistic conservation of angular momentum. How do we prove Noether's theorem? Well, you prove it by counterexample. Actually, there's a formal way of proving it using what we call the action principle, Lagrangian dynamics, calculus of variation. It's very sophisticated. But you can get the drift of the theorem very easily. Let's suppose we have the Acme Energy Company, power company, and it's based on the discovery of some inventor that Tuesday mornings at 10 a.m., gravity is 10% weaker than it is for the rest of the week. At 10 a.m., suddenly gravity becomes 10% weaker. It stays that way for a while. If you come back Wednesday, it's gone back to its normal value. And the inventor invented a G meter that measures gravity and made this discovery. So the Acme Energy Company is formed by a bunch of investors, and they float stock, and they go public, and a lot of people start buying the stock, and the insiders who started it are very wealthy, because what they're going to do is build a power company. They're going to have a water turbine generator, and they're going to pump, on Tuesdays at 10 a.m., they're going to pump water up in a water tower. That costs them energy, which is minus the mass of the water times the value of little g on Tuesday times the height of the water tower. Okay? And then the next day, Wednesday, when g has gotten bigger, they're going to drain the water out of the tower, and they're going to get back energy m times g on Wednesday times h. And the G meter says on Wednesdays that g is bigger than it is on Tuesdays. And so they've gotten energy from nowhere. They got a net energy gain of m g Wednesday minus g Tuesday times h. And this is a tremendous breakthrough. It solves the world's energy crisis, and the company's stock immediately starts going up. You know, countless widows, orphans, and people start investing in this, and stockbrokers get in it, and so forth. And then suddenly, hush hush, the inventor flees the country. Can't be found anywhere. Hopped a red-eye flight somewhere into some obscure place. And lo and behold, the insiders of the company had already sold all their stock. And the Universal Testing Laboratory has tested the G meter and is about to announce the results. Well, you know, the week before something like that, the stock goes up, then it goes down, then it goes back up, and it oscillates wildly. Finally, Monday morning, the UTL has its public announcement that says, we have discovered a flaw in the G meter. It turns out that Tuesdays at 10 a.m., the nearby town of Batavia tests its air raid sirens, fearing an air raid. The acoustic vibrations of the noise in the air causes the G meter to read a false result, 10% lower. And then it takes about a day for the spring to relax back to its normal value. So G Wednesday minus G Tuesday is actually truly zero. There is no net energy gain. Energy is conserved. Now, this is, you know, facetious, but this happens all the time. It happens all the time on Wall Street. It happens, people are making this mistake right now with corn ethanol. They're putting more energy in than they're getting out. When I was a graduate student, there was a company that made, in California, that made motorhomes. And motorhomes were very popular back then. And suddenly they announced that they could break water down into hydrogen and oxygen. And a little bit later, they could combine the hydrogen and oxygen and it would burn, and you would get energy out, and they would get a net energy gain, and you could fuel cars this way. And in particular, you could now haul very big motorhomes across the country. You see, that was when gasoline was first starting to go up in price. And I came into Caltech's theory group that morning, and Richard Feynman was in a really excited state. He says, how can I short every share of stock in this company? Because it's based on the false premise that water molecules are somehow different in the future than they are today. Otherwise, energy is conserved. You won't get any energy out. I actually went to lunch with Feynman that day, and we talked about the Security and Exchange Commission had already suspended trading in the stock, but you could buy put options. They had, for some reason, suspended that, and I looked it up, and sure enough, we could buy put options. The stock had gone from $1 up to $20 a share. If we bought put options at 20, the stock would go way back down, and we'd make an enormous profit. That was the theory, and I was explaining this to Feynman. He said, this is great, let's do it. What do we have to do? And I said, well, we got to get some forms from the broker to get permission to trade puts. And he said, oh, forget it. I'm going to go back and do my physics. Well, it turned out that was the right thing to do, because even though this was a complete scandal and this company was simply in violation of the law of energy conservation, the stock never really went back down. It sort of drifted down a little bit, but we would have never made any money off these put options. So while the law of energy conservation and the invariance of the laws of physics in time applies to physics, it doesn't apply to the stock market. But these scandals happen all the time, and total misunderstanding of the energy budget of a system it's very easy to get confused because there's so many ways energy can leak out of the system. I mean, think of a car. When you're driving down the highway, yes, you're moving the car, but you're also heating the engine, radiating energy and heat. You're compressing the tires, which get hot. You're radiating energy that way. There's, of course, aerodynamic resistance. There are all these, there's noise. You're making sound. That's energy. All this energy is radiating away from the system. And so if you're not careful, you'll think somehow you're losing a net amount of energy or something. It all balances out. The total energy that you're starting with in the fuel is equal to the total energy that's produced, motion plus all the losses. Momentum conservation is also complicated. You can have a very high momentum object collide with a planet, and you get a very messy intermediate state. But sometime later, the planet and the comet all recombine, and you have exactly the same total momentum initially as you have afterward, no matter what collision it is, no matter how complicated. Angular momentum conservation is probably most readily demonstrated by the way a gyroscope behaves. While it's spinning in free space, it'll always preserve its angular momentum. You have to exert a torque, which is a combination of force and distance, to change its angular momentum. And you know how gyroscopes have a funny behavior when you start playing with them, which is because you're fighting angular momentum conservation. You try to move the position or orientation of the gyroscope. And you can see it here with the spinning professor holding the two dumbbells, who then pulls the dumbbells in. To conserve angular momentum, you have to increase the velocity of spin, the angular velocity. In fact, it goes quadratically. If you have this distance, you need 4 times as much spin. And so, in fact, you see this rapid spin up, and it's sort of impressive, and ice skaters know this, and it's just the conservation of angular momentum. But in some sense, the most important symmetry of all, and the thing that really launched modern physics, and I don't have the time to go into it in detail, is the principle of that the laws of motion are the same in any state of motion. And in fact, the theorem we get from that is that if you have an object just moving uniformly through space, empty space, if you don't do anything to it, if you don't exert a force on it, it will continue to move in a straight line at the same velocity forever. This was a very difficult concept. The ancient Greeks were not able to get this concept because they lived in a friction-dominated world. And as long as you live in a friction-dominated world, the equation you're going to get is, in some sense, force equals mass times velocity. You know, something's big and massive. To get it to move, I have to apply a force. If I stop applying the force, it stops. If you have wagon carts with wheels that don't have the best bearings, and I know they didn't back then, then you stop pushing, it stops. You should go to Pompeii sometime and look at the ancient Roman streets of a busy city. And what you'll see, often the streets coming downhill to an intersection, those streets are built of massive rocks that the Romans nicely put together and flattened out. But as you approach the intersection, you'll see these deep wagon ruts. Those wagon ruts are these heavy carts that actually start rolling, starting to stop at that point, and the friction has dug these ruts into the pavement. It's quite impressive. You see it graphically at Pompeii. So they had potholes in Rome too. But basically the notion of something continuing to move by itself without a force applied to it was something they couldn't grasp. And it was so difficult that even when we had Copernicus's theory that put in the late 1500s, where the sun was at the center, and Kepler had gone in and understood that the motion was not circular. I mean, there was almost a religion for 2,000 years about the circle. Religion believed it had to be circles, those orbits, and they weren't. They were ellipses with the sun at a focus. And Kepler got the exact laws of motion, and still people did not understand the law of inertia. And it really took Galileo, Descartes, and others to understand that it wasn't the pushing of the planet in its orbit that was relevant. It was what was causing it to move away from a straight line. And once you figured that out, you could get to Newton. Newton's first law, which distills what people had figured out in the previous 100 years, is that an object remains in uniform motion unless acted upon by a force. And what that really means is all states of motion are equivalent. If there are no forces around, the object will continue to move in the same state of uniform motion. And if you're riding with it, you don't notice anything different about the physical world than somebody who's staying at home not moving. That what really happens is the force changes the velocity. And so it's not velocity that appears here, it's acceleration. And then the force that 1 exerts on 2 is minus the force 2 exerts on 1 is actually, and it's tricky to see it, but it's actually due to the translational invariance of the laws of physics. So these symmetries are already encoded into Newton's laws. Here's translational invariance, and actually this equation is rotationally invariant because that force is a vector pointing one way and the acceleration points the same way as the force. And I can just rotate the system and the equation stays the same. So all of those symmetries of space and time are encoded into these laws. And then Newton took the big step of telling us what the force really is. See, he has this equation that almost means nothing until you tell me what the force is. It means that force causes change in velocity, not position. But the force, he figured out, is the inverse square law force, the universal law of gravitation. And then he invented the subject of calculus. So he could solve the mathematical problem of what is the solution to this equation when this is the force. Starting with something with some initial velocity, how does it move? And he proved it was an ellipse, and he proved Kepler's laws were correct. That's enormous progress, and this is the beginning of the scientific modern era. So now, this question of, see, the symmetries are really buried in here. It's a little hard to see them. This symmetry, the fact that this is related to the equivalence of all states of motion is subtle, but it is. The fact that this is related to the conservation of momentum is subtle. You have to prove momentum conservation from this rule. And Einstein really turned it on its head. And he said, let's think directly about the symmetries. So, what I want to show you is how the symmetry of motion and Noether's theorem leads to antimatter. But in order to do that, I have to teach you relativity. Have you had the lecture on relativity yet? Okay, well, I'm going to give you it again, but in a much different form. And I'm going to do it in all of maybe 5 or 10 minutes. And then maybe you'll have a deeper insight into it. Relativity was not born with Einstein. Galileo realized that it is the symmetry of motion at a different level, the level of classical physics, that defines modern physics. And it's built into this law of principle of inertia of Newton's first law. So what did Galileo say? This is effectively what he said. He said, let's say we have two observers, two people, and they're going to make their own coordinate systems. And they're going to measure position in that direction with the coordinate axis x, and they're going to measure time with a clock. So let's suppose there's another observer who's moving along relative to the stationary observer at some velocity along the x-axis. So if there's an object that he says is fixed at some value of x, I'm carrying a coordinate system with me, okay? And I'm going this way, and I'm seeing my value of x prime for that object. So here it is. My value is becoming negative. It's changing. So my value of the coordinate of this thing, here's my coordinate value, as I move, is changing. Whereas as he sits there, it's fixed. And so what's happening is my value is his value minus my velocity times time. If I'm sitting at rest, my x prime, x coordinate for that thing, is fixed. X prime just equals x. But if I start moving, it starts changing. So I see a tree outside the railroad car window. For the person who's not on the train, the tree is sitting still. For me, the tree appears to be moving. That's all that says. But the core idea of classical physics was that we will carry clocks. He'll have his watch, I'll have my watch, and we'll be able to set them to measure seconds, and we can agree to start them at t equals 0 and let them tick. And no matter how I move, I can look at my clock and I can say, hey, what time is it? And he'll say, oh, it's 12:05.75. Yep, it was 12:05.75. Time is universal. The moving clock and the stationary clock have exactly the same time, whereas motion of position changes. That's the symmetry transformation law between x and t and x prime and t prime. Remember we did that up here for the sphere. We said, got a set of coordinates for one observer, and then we rotate the observer. By rotating him, we get a new set of coordinates, x prime, y prime, z prime, but we're still living on the sphere, so that and that give the same value for a sphere. They both live in the radius 1 of the sphere. Okay? The transformation law is some messy relationship between x, y, z, w, x prime, y prime, z prime, and w. Well, this is the relationship of x prime and t prime for x and t in physics, according to Galileo. This is called classical physics. Now, Einstein was faced with something else. He began to think about time. And one of the things that this predicts is that if he shoots a photon, particle of light, at the velocity c in that direction, if I start running after that photon with my velocity v, I should see it moving slower. I should see it moving with the velocity c minus v. If I run at the velocity of light, I should have caught up with the photon, high photon, running along with me. And if I go faster than the speed of light, I should see the photon moving behind me. That's a direct prediction of this rule. Now, to make the long story short, an experiment was done around the 1880s that showed that that doesn't happen. If he launches a photon at speed c, and I run after it, no matter how fast I run, I always see it escaping at speed c. It's almost like I'm in the twilight zone. No matter how fast I go, I can never catch the photon. It's always moving at the speed of light. So faced with that, Einstein had a problem. Basically, if I have a flash bulb go off at position x equals 0, t equals 0, photons will travel out. And photons are the special ones for which the speed of light times, so here's a future event, let's say, at which a photon is received. In order for a photon to be received here, the speed of light times the distance x, times the distance times t, must equal x. In other words, c times t minus x equals 0. But the photons will also go in the opposite direction. So there'll be photons at minus x. So ct plus x equals 0. And if I just multiply these two things together, I get ct squared minus x squared equals 0. That's the equation of motion of all photons. If I'm an observer in a new system running after photons, I'll use my new coordinates x prime and t prime. And if I want to insist that light moves exactly the same way relative to me at the speed of light, then it must be true for me that c squared t prime squared minus x prime squared also equals 0. In other words, all I told you is the equation of motion of light is this for me, but there's nothing special about me sitting still. For a moving observer, you better get the same equation of motion for light. This is the important thing that doesn't change. For Galileo, this was the thing that didn't change. For Einstein, this is what doesn't change. So this is sort of like a sphere. It's like SO2. It's like x squared plus y squared equals 1. And we know that cosines and sines relate x and y to x prime and y prime, such that x prime squared plus y prime squared equals 1. So Einstein is faced with the question, what transformation law connects this to this? And by the way, you don't even have to talk about photons. You can talk about a distance between events in space-time called tau. That's any c squared t squared minus x squared. And the symmetry of space-time is that this funny new type of distance in space-time should be the same for all observers. So once you say that's the symmetry principle, the rest is algebra. And now it's easy, you can do it yourself with little effort, to find a transformation law that gives t prime and x prime in terms of t and x for any for some thing we'll call v. We don't know what v is yet. But what Einstein found is that if you substitute this x prime, where gamma is this 1 over root 1 minus v squared over c squared, and this t prime into this equation, you'll get back this equation. Okay? Take this t prime, this x prime, substitute this formula for t prime here, formula for x here, do the algebra, and you'll get this. Therefore, the relationship between observers that preserves the way that light is seen to move, that it's always the same velocity, is this symmetry statement, not this one. And this transformation law is now replaced by this one. But notice, suppose this thing we call v is small compared to the speed of light. if v over c is small, this thing gamma, this messy 1 over root 1 minus v squared over c squared becomes 1. And this becomes t minus 0. T prime equals t when the velocity is small. What happens to x? Well, gamma becomes 1, and I get just Galileo. So these contain, for small velocity, Galileo's law. It's only when the velocity starts to approach the speed of light, the relative velocity of motion of two observers, that funny things are going to start to happen. Do you understand? This is exactly like saying I have the symmetry of a sphere and finding a relationship between an x prime and a y prime and an x and a y, and showing that x squared plus y squared equals x prime squared plus y prime squared equals 1. The concept of distance in space-time involves a minus sign. Okay, how much time do I have, Roger?
12 minutes.
Oh, thank you. Good. That's very gracious. What do we do about energy and momentum? So here's the conundrum. In Galileo's symmetry, things happen to space, but they don't happen to time. So there's really an asymmetry here between time and space. Time is absolute in classical physics, but space is not. You can move relative to another observer, but you're all stuck with the same flow of time. That's what Galileo is saying. And if we write down the momentum of a particle in classical physics, it's the mass times the velocity. And remember, momentum has to do with spatial translations in space. Its conservation law comes from space translations, according to Eminov. If we work out the energy of a particle in classical physics, it's 1/2 mv squared. And I can write a relationship that just eliminates v. Energy equals momentum squared over 2m. This is a very asymmetrical formula between energy and momentum. But that's not surprising, because Galileo told us there's a very asymmetrical behavior of space under boosts and time under boosts. Time doesn't change, space does. So we get energy to the first power, momentum to the second power. That's what we get. And it works. It works very well in classical physics. But Einstein is telling us that space-time has a symmetry, a geometry, if you like, in which if you have an interval between two events in time of t and an interval of x, c squared t squared minus x squared will be the same for all observers. In particular, if tau is 0, that describes the motion of light, so all observers will find the same speed of light. How do we get a relationship between energy and momentum in relativity? This is what we had in classical physics. E is p squared over 2m. What do we do in relativity? Well, we remember Eminowther's theorem, which tells us that energy comes from the invariance of the laws of physics and time. Momentum comes from the invariance in space. So there must be a more symmetrical relationship between energy and momentum. You can think of the speed of light as just a thing that calibrates time and space. You can just take the speed of light to be 1 and use light seconds for distance and seconds for time. And you see this is much more symmetrical. Time squared minus x squared equals an invariant. So now energy squared minus momentum squared must equal an invariant. Einstein had to guess what this invariant is. Okay? It starts as a guess. So let's just guess that it's got to do with the mass of the particle and the speed of light. The speed of light is just getting all the units right. It's getting all the physical dimensions right. So this is the relationship now between energy, momentum, and mass. And what it means is, if you're moving, let's say you made a top quark at Fermilab. You measure its energy, and you measure its momentum. You take its energy squared minus its momentum squared times c squared, you'll get its mass, the mass of the top quark squared times the speed of light to the 4th power. What if you make a top quark going at a much higher energy at the LHC? You'll get a much different energy and a much different momentum. And that's what's seen by an observer in a much different state of motion relative to here at Fermilab. It would be an observer who's been boosted relative to the slower top quark that we would make. But it's still true with the new energy of the top quark at the LHC And the new momentum, if you substitute its energy squared minus momentum squared c squared, you still get the top mass squared times c. So that is the defining symmetry. That's this symmetry plus Noether telling you how energy and momentum are connected to space and time. It's the corresponding dual symmetry condition for energy and momentum. But notice something weird now. It doesn't just give you the energy. It gives you the square of the energy. So to calculate the energy, we have to put momentum squared plus c squared on the right, on the left-hand side over here. E squared equals p squared c squared plus m squared c to the fourth. Then we have to take the square root. And now you see why Einstein guessed this had to be right. Because if you take the square root, you get a constant term, plus you get a motion term, p squared over 2m. Plus you get higher order terms that go like 1 over high powers of the speed of light, which you wouldn't see if the system is moving slowly. And so apart from this thing, Einstein has recovered Newton's relationship for small velocity objects. But he's gotten something really incredible as well. He's found that energy for a resting object is not 0. It's mc squared. E equals mc squared comes from the space-time symmetry that defines inertia, defines the states of motion, transcribed into an equivalent statement for energy and momentum, solving it, and then matching, if you like, this to this, predicts this. And now we have the nuclear age. You know, we can take a nucleus of one mass and break it apart into pieces that have smaller masses. And the energy really does come out as the difference in the initial masses minus the final masses times c squared. That's not bogus like the Acme power company. That's called a nuclear power plant. So we can really do cool stuff with this. Now, are you suspicious of this at all? Is there something peculiar here? Anything bugging you about all this? You know, notice how much work you had to do to get the energy. Notice this square root. What's the funny thing about square roots? Anybody have a thought about square? What's the square root of 4? What's the square root of 4?
Plus or minus 2.
Ah. You said plus or minus 2. I just put plus 2 here. What's minus 2? What do I do with the minus? Einstein's theory is predicting something really bizarre. It's predicting negative energy. There has to be both positive and negative energy. So if I have an electron, it can be sitting still, and it has energy equals m electron squared c squared. And if I move it, it's got kinetic energy as well. It ought to be possible to have an electron sitting still, according to this, with negative energy. And people began to sweat this fact. First of all, this is a disaster. It's a disaster because if you got a hydrogen atom with an electron sitting there in the ground state orbiting the proton, electron has positive energy, proton has positive energy. That's not the ground state anymore because the electron could hop down to a Bohr orbit with minus mc squared plus kinetic, with negative kinetic energy as well, emitting a really energetic gamma ray, a gamma ray with 2 mc squared of energy. Now you got a hydrogen atom with a negative energy electron, and now it just starts gaining energy, because if gaining motion energy, because it gets more and more negative energy. If I increase p, the momentum, I still have an overall minus sign. The thing keeps losing energy as it accelerates, radiating radiation. It gets worse and worse. All things would be unstable. Even the proton at the nucleus would jump down into a negative energy state, and everything would start moving and getting more and more negative infinite energy. The world would collapse. Complete disaster. There's no stable theory, no stable world. Looks like we're at a dead end. The very beginning, I told you about the electron being a spinner. And I told you because spinners are square roots of vectors. It's a very peculiar behavior. But you have to rotate them not through 360 degrees, but you got to rotate them through twice 360 degrees to bring them back to themselves. And it turns out that means if I put 2 electrons in the same state, and I just swap their positions, it's the same as rotating this guy through 180 this guy through 180, and therefore that state equals minus itself, so that state is 0. It cannot exist. Electrons cannot be put in the same physical state at the same time. You can put two electrons in the same state of motion. Spinors are either up or down, spin up or spin down. If the first electron goes in up, the second goes in down. That's what happens in helium. And you can't put any more electrons in that state of motion. You got an up electron, a down electron going around the nucleus. No electron will hop in there because the states are filled. The exclusion principle is due to the weird spin of the electron. So there was a really brilliant, one of the most brilliant physicists of the 20th century, Paul Dirac. The string theorists will tell you he was the most brilliant because he thinks the way string theorists think. And really remarkable guy, mathematician and physicist. And he had a brilliant idea. He said, well, suppose all these negative energy levels of any momentum go all the way, it's a big ocean, it goes all the way down to negative infinite momentum. Suppose they're filled. Who says what a vacuum is? I'm going to say a vacuum is a state in which all the negative energy states that Einstein says are there are already occupied. Each level here has one spin-up electron and one spin-down electron. My vacuum is a humongous helium atom. It's or argon or krypton or whatever inert atom. The vacuum is chemically inert. All negative energies are filled. Now I'm home free, because if I have an electron up here of positive energy, and it tries to jump down into one of these states, the state's filled already. Can't do it. I've stabilized the world. Dirac went to bed that night thinking, great, we now know how it works. And he wrote down the relativistic theory of the spin 1/2 electron. He now knew how to interpret it. But the next morning he woke up with a hangover. And he realized something weird will happen. I can take an electron that's already in the ocean, like a fish, part of the vacuum, and I can pull it in the boat. If I kick the vacuum hard enough, just the vacuum, empty space, I go and kick the vacuum. He thought he'd hidden it completely from view. But he realized if you kick it hard enough, under the right circumstances, you can conserve energy and momentum. You will kick an electron out of the vacuum from negative energy to positive energy. Because this has negative energy. Now, when that happens, it leaves an empty slot in the vacuum. Got to now think double negatives here. An empty hole in the vacuum is the absence of negative energy. So the hole in the vacuum behaves as though it has positive energy. The hole is also the absence of a negative electric charge, as electrons have. Therefore, it behaves like positive electric charge. Therefore, what Dirac is saying is if you, under the right circumstances, hit the vacuum, you'll make what looks to you like an electron with positive energy and negative charge, and a hole, an absence of a negative energy, negative charge, a positively charged mirror image of the electron, a positively charged positive energy. So it costs a certain amount of energy to yank this guy out of the vacuum, and when you have, you'll see what looks like a pair of particles. One positive charged particle and one negative. And here it is. A few years later, the first observation of the electron and the positron, and I don't know which is which. One is the electron and one is the positron. They've got a magnetic field here which would normally curl an electron going this way like that. If that were an electron, it would curl the opposite way here, but it's curling like that, which tells you it's positive charge. And so Dirac predicted, this is like the 9th symphony of physics in the 20th century. You have this marvelous stuff from Haydn to Mozart to Bach to Haydn, Mozart. Finally along comes the master Dirac, puts it all together, and makes the greatest prediction of all, that there must exist antimatter. Look what led to it. Galileo, changing the definition, who said this is the symmetry, time is absolute. Einstein, who said no, this is the symmetry, the speed of light is absolute. Therefore, the transformation laws are modified. Therefore, the relationship between energy and momentum is modified. Noether's theorem that tells me how to modify the law. So I've got a symmetry in space, time, I've also got a symmetry in energy momentum. gives me the new result that m equals mc squared for particles at rest, plus motion, which agreed with what Galileo and Newton could perceive, but is now a mere correction to this enormous piece. And then the bizarre consequence that the square root had to be taken, which is minus signs. The even more bizarre notion of electrons as spin 1/2 spinners that change sign when you rotate them through 360 degrees, meaning you can't put two of them in the same state at the same time. Pauli exclusion principle, which explained the whole periodic table of the elements. And now Dirac says our vacuum is full of these things. And now you will make a positive energy electron and a negative electric charge and a positive energy hole with a positive electric charge. Look at what a climb that was. And we do it every day at Fermilab. So we make a top quark and an anti-top quark, a bottom quark and an antibottom quark. We yank them out of the vacuum. We're fishermen. We go down deep, we yank stuff out of the vacuum. And what we're wondering now is what's much deeper down in this big ocean down. What other stuff is waiting to be pulled out of the vacuum? Okay, they're all yours, Roger.